In this section, we want to focus on the convergence of real sequences, so sequences of real numbers. In the real numbers, we have the advantage that we have this ordering. We have a total order on R, we have this, and there we can kind of use some tricks for real sequences that don't work for complex sequences, and I want to focus them on them in this section. This also gives you to some nice new examples that we will see throughout this section, and we will just go through one by one. Okay, so to start, I want to first give some examples about sequences of real numbers involving roots of real numbers, and yeah, of non-negative real numbers to be precise. But to do so, I'll just prepare one little statement about roots that I haven't, basically I just omitted when I introduced them. Namely theorem 222, that, n be an integer, non-negative integer, positive integer. We have two real numbers, x and y, with both non-negative, and we want x to be smaller than y. Okay, then it holds that the nth root of x is smaller than the nth root of y. Later on, we will call this property strictly monotonically increasing, but this will take a while until we do this. I will do this now explicitly. So that this kind of taking nth roots preserves inequalities. Okay, the proof of this. So assume this was not the case. So assume there was an x in n and numbers x and y satisfying these inequalities with such that the nth root of x was bigger than or equal to the nth root of y. Since roots are always non-negative, so the nth roots of x and y are both at least 0. This implies, because we know that powers with inequalities preserve inequalities, just the properties of ordered fields. So if we kind of take an exponents here, so some positive exponents here, this will preserve the inequality. So this then yields that x, which is nothing but the nth root of x to the power of n, this must then also be bigger than or equal to the nth root of y taken to the power of n, which is of course nothing but y. And there we already have the contradiction, since we assumed that x is smaller than y, so this already shows the statement. So we know that this property holds. Okay, using this property, we can now discuss some very important example that will also be needed very often in this course, I think. Example 223, namely the limit of the sequence 1 over the qth root of n to the power of p for some numbers p and q, which can also be written as the limit and n to infinity, of course. This can also be written as the limit n to infinity of 1 over n to the exponent p over q. This is always 0. This for all p, q in n, where the 1th root, so q equal to 1, this is just supposed to mean the number itself. So where q, the root 1 over x is just defined as x itself. Okay. So we have seen that 1 over n goes to 0, and this is kind of a very general thing. Now important that we have a positive rational exponent here. Then we always get that this limit is 0. Okay, let epsilon be some positive number. So then there exists, and this was part of chapter 1, there exists an n0 in n with 1 over n0 is smaller than some positive number, and now we don't take epsilon itself, but we take epsilon to the power of q to the p. Okay, then it follows that 1 to the qth root of n0 to the power of p, this is then, so this is the same as 1 over n0 to the power of p to the q. So by the power rule, strictly the power laws and the words how to compute with powers, I haven't proven them yet. I will prove a general version of them when we get real exponents, but we will come to this later. So this I haven't, but we can use this roots of computation that we're familiar with from high school. So this really holds, and now since this kind of roots and powers, and we've seen it both preserve inequalities, this is then, so by theorem 222, this is then smaller than epsilon to the q over p to the power of p over q, and this is just epsilon. And this implies that 1 over the qth root of n to the p, if n is now big enough, so this is of course the absolute value, doesn't matter, this is 1 over the qth root of n to the p, that again this is then smaller than or equal to 1 over the qth root of n0 to the p, again by theorem 222, which is smaller than epsilon as we've just seen, if n is big enough, i.e. if n is at least n0. So this already shows that the limit n to infinity of 1 over n to the power p over q is 0. Okay, so this is one interesting example. And for two more interesting examples, I will put in a theorem because the proofs require a bit more effort. But they are also kind of quite natural limits that you often consider. Theorem 224. So, first of all, we take some positive number, a bigger than 0. And now we investigate the sequence, taking the nth root of a and now letting this n go to infinity. Here we had some fixed exponents, now we kind of let this exponent converge. So what happens here? This goes indeed to 1. Second part, another sequence that you can write in this way, namely not taking the nth root of some fixed number, but taking the nth root of n. What happens here? This also converges to 1. So these are important examples. So for part A. Okay, we first consider the case that A is 1 or bigger. The second case we'll then treat it afterwards, so if A is between 0 and 1. So if A is at least 1, then you can see that the nth root of A is also bigger than or equal to 1. This is simply by taking powers you can, from the laws of ordered fields. So this holds true for all n in n. Okay, if we got this, we do the following trick. We put now xn to be 1, other way around, nth root of a minus 1. So we want the absolute value of this to go to 0, and of course the absolute value here doesn't matter because by this term is always non-negative. So we need to show so that xn really goes to 0. So need to show that the limit of xn is 0. And this we can now do with a computational trick. Namely, we can again use Bernoulli's inequality, which I always find quite refreshing, so to say, because this inequality is kind of, when you see it first, it looks not that interesting, but it has surprisingly many applications. Namely, by Bernoulli's inequality, we can make a nice little estimate. Namely, consider the number a. If you want to express a in terms of xn, this is simply 1 plus xn to the power of n. Right? So 1 plus xn is simply the nth root of a to the power of n, we get a. So to this is now the Bernoulli situation. So this is then, because xn is in particular bigger than or equal to minus 1, we can apply Bernoulli. So this gives a lower bound by 1 plus n times xn. And this holds true for all n in n. And if we play around with the terms a little bit, this shows that xn is smaller than or equal to a minus 1 over n. If we just take this in this part here and just juggle around the terms, this is of course smaller than a over n for all n in n. Okay, now nice start. This is what we use now for the convergence proof. And now we take some epsilon bigger than 0. And here we know that there exists an n0 in n such that 1 over n0 is smaller than epsilon over a. Yes, it's one of those proofs again. So this n0 we have. Then this difference here, the nth root of a minus 1 to the absolute value, this is simply xn. Okay, we know that this is bounded from above by a over n. And if n is now big enough, so if n exceeds this n0, this is in fact smaller than or equal to a over n0, which is smaller than, by this estimate, a times a over a. Et voila, we get an epsilon for all n at least n0. And since epsilon was arbitrary, this shows the thing. Okay, and the case, so this is for the case a 1 or bigger. If 0 is smaller than a smaller than 1, then a to the minus 1, so its inverse, will be bigger than 1. And the trick is now to work with the inverse here instead. Namely, then we get the limit of the nth root of a is then, by taking double fractions basically, you can show that this is the same as the limit for n goes to infinity of n over, and then here the nth root of a minus 1 in the denominator. And here we know that this converges to 1 because this was the first case. And by the limit rules that we had, this again gives 1. So this completes the proof of part A. Okay, for part B, I just need to erase. Okay, in part B, we want to show this equation as a quick reminder. And it turns out the same trick we used in A, it just doesn't work. But we can use a similar thing, and we follow basically the same approach, but with a different computation, which is a bit more intricate. Namely, we do a similar thing as before. We put again xn be as the nth root of n minus 1 for all n in n. Okay, now we want to find a good estimate, similar to what we did before. So an estimate for these xn. Here we cannot use the Bernoulli's inequality anymore, but we can use another theorem that we had before, namely the Binomial Theorem. As we shall see immediately. Again, as before, we can use now a similar trick. We know that n is the same as 1 plus xn to the power of n. This follows immediately from its definition. So 1 plus gives just the nth root of n to the power of n, we're done. And so, okay, here we cannot use directly Bernoulli, or we could now apply Bernoulli, but it wouldn't lead us anywhere. But if we take the Binomial Theorem, the binomial says something about the powers of a sum. And in this case, this means that we get that this is the sum from k equal to 0 to n. Then we get these binomial coefficients n choose k of, and then the first factor, first summand to the power of k times the second summand to the power of n minus k, xn to the n minus k. As you see, the summand 1 to the k is irrelevant, this is always 1. And what we now do is to take the last three summands of the sum and write them down explicitly, namely the case n minus 1, and n minus 2 here from this sum. So this means if we first take k equal to m, we would get n over m, n choose n. So this is just 1, and here we would get xn with exponent n minus n, which is naught. So here is nothing happening, we just get n choose n. Next thing, for k equal to n minus 1, we get n choose n minus 1. Here we get 1, and here we get index 1, so we get this. And next thing, we get n choose n minus 1. and we get xn to the power of 2, and the rest of the sum we leave as it is. So this would be then the remaining sum from 0 to n minus 3 of n choose k, 1 to the k, you don't need to write that down, xn to n minus k. Okay, so now we need to compute this binomial coefficients. We haven't used this explicitly, so I will just do the computation quickly. N choose n. What is this? This is n factorial divided by n factorial times n minus n factorial, which is 0 factorial. 0 factorial is 1 by definition. These cancel each other out, so this is just 1. Okay, n choose n minus 1. This is n factorial divided by n minus 1 factorial times 1 factorial. 1 factorial again is just 1. Here we have n times n minus 1 times n minus 2, and here we have n minus 1 times n minus 2, and so on. So almost everything cancels out, and the only remaining factor is n. And for n choose n minus 2. N choose n minus 2. This is n factorial divided by n minus 2 factorial times 2 factorial. 2 factorial is 1 times 2, which is 2. And here we just get that here, dividing this, we get that here we have 2 more factors, and this just gives n times n minus 1, and in the denominator we just get 2. So this shows that inserting this now in this computation, n is the same as 1 plus n times xn plus n times n minus 1 over 2 xn squared plus the sum from k equal to 0 to n minus 3 n choose k xn to the n minus k. Okay, we know from basically the same argument as before, we can show that these guys here are always non-negative. Taking a look at this equation, we only get these binomial coefficients are by definition always non-negative, so everything, all of the summands are non-negative. So this means we can just estimate this from below if we just drop some of the summands, which means this is then bigger than or equal to, and now I will just keep a few of them. 1 plus, and now I keep this, n times n minus 1 over 2 xn squared. So here it follows that n has this property. Okay, this now gives an estimate for xn if we just reorder the terms in this inequality. Namely, in this way we get, so here we first subtract 1, so we get here n minus 1, which means we have 2 factors of n minus 1, which we can just, which cancel each other out. And this then gives xn squared is smaller than or equal to 2 over n. Yeah, right. So since we know that this is non-negative, so that xn is non-negative, this then means that xn, so taking the root, is then smaller than or equal to the root of 2 over n, again by this theorem 222 that we just had. So we take the roots on both sides, and since xn is non-negative, we know that this is indeed the root of this. So here, theorem 222, I don't write on this again. But here again, we have some estimate for xn, which is helpful. This for all n in n. Okay, and using this estimate, we can now proceed similar as before. We take epsilon bigger than 0. Then there exists an n0 in n with, and this time we again choose it suitably such that 1 over n0 is smaller than epsilon squared over 2. Okay, namely, then we get that for all n at least n0, the nth root of n minus 1 to the absolute value, this is just xn, since the term is non-negative. This is smaller than or equal to the square root of 2 over n, which we have seen before. This is then, so here it's again theorem 222, smaller than or equal to the square root of 2 over n0. And then we see that this has been suitably chosen so that this is, this is smaller than the square root of epsilon squared. And since epsilon is positive, this is epsilon. And so this shows yeah, this completes the proof. We have shown for every epsilon that we have such an n0. So the limit of n to infinity from the nth root of n is 1. This gives us two nice limits. That was a bit more effort. Okay, so we've computed now some important limits from some really common sequences. Okay, the next thing we want to tackle is, so this was so much about roots. The next thing we want to tackle is about using inequalities in a smart way and using estimates in a smart way. And for this, I first introduce some terminology, and then you will see what I mean when I say using inequalities nicely. Okay, first of all, some very elementary property. This is just for every sequence in a set. X is a set, an a sequence nx, and we say that the sequence an has some property, so has a property that we're discussing, and we say that this has a property for almost every n in n. So almost every is of course not precise, so that's why we need to define this. If all of this an, with the exception of finitely many, if all but finitely many of the an have this property. So this means, like when we study convergence and so on, or when we study sequence and convergence, we always try to let n to be very, very, very big. And if something holds for only finitely many, we know that there is some point where we've passed the point where this is not occurring anymore, or the exceptions are not occurring anymore. So from some certain point on, this is another way you could reformulate this. So there is some n0 such that from this n0 on, every element has this property. And this is, if we study convergence and so on, it doesn't matter when finitely many of the elements do some things that we don't like. This is kind of irrelevant. Okay, so we will use this notion in the first theorem about inequalities and convergence. Namely, if we have two convergent real sequences, an and bn, convergent real sequences, if there is an inequality between them, namely if an is smaller than or equal to bn for almost every n in n, then it follows that there is an equality between the limits. Then the limit of the an is also smaller than or equal to the limit of the bn. Okay. There's really this nice inequality. So let's prove this. First of all, we give names to the limits. So again, we are very creative and call the limit of the an a, and the same thing with b for the limit of the bn. Okay, so we know that this property, this inequality holds for almost every n in n. So it means from a certain value on, this always holds. This means we have some number we call n1 in n, such that an is smaller than or equal to bn for all n bigger than or equal to n1. Okay. Now, let epsilon bigger than 0 be an arbitrary number. Then we know, because of convergence, so there are n2 and n3 in n, such that an minus a to the absolute value is smaller than epsilon for all n2 or bigger. And the same here for the bn's and b. This is smaller than epsilon for n bigger than or equal to n3. Okay. And now we take, again, n0 to be the biggest of the numbers we've studied yet. So the maximum of n1, n2, n3. Okay? Then we get especially a minus epsilon. This has to be smaller than an. This is because of this equation here. So in particular, this needs to hold. So this is the first step. The next step would be that we can now estimate that this is at most Bn, but we also know that Bn and B differ at most by epsilon. So we know that this is smaller than B plus epsilon. Okay, this is a chain of inequalities. So this means A minus epsilon is smaller than B plus epsilon, and this is of course equivalent to A minus B is smaller than 2 epsilon. Okay, but epsilon was arbitrary. Since epsilon was arbitrary, and we have seen already in the proof of uniqueness of limits, I think it was. Sorry, I just confused something, that's why I had to cut. So if this holds for every arbitrarily small number epsilon, then you can easily derive that it holds that A minus B is smaller than or equal to 0. Because for every, we could get arbitrarily small, otherwise this couldn't happen. But if this holds, this is equivalent to A smaller than or equal to B, and this is precisely what we wanted to show, this inequality between the limits. Okay, so this means limits preserve inequalities in this sense, which is also good news, so this gives us new ways of computing later on. We will now see a very powerful theorem about inequalities and limits, and I will erase for that. Before I come to the next big theorem, there's just one little consequence of the previous theorem I want to state explicitly. This is not very spectacular, but this is a form of the theorem that is used quite often, or that is really useful. Corollary 227. So if we have a convergent real sequence, so two cases, and we have some fixed number C in R. Namely, if an is smaller than or equal to C for every n and n, sorry, not for every, for almost every n and n is enough. For almost every n in n, then it follows that the limit of the sequence is also at most C. So the limit is smaller than or equal to C. Same thing with reverse inequalities. If an is bounded from below by C for almost every n in n, then the limit will also be bigger than or equal to C. Okay, yeah, this is now really a special case of the previous one. So this is, yeah, maybe I can add this one line. This follows from the previous theorem, so it follows from theorem 226 by just letting one of the sequences be constant. You just take the constant sequence C as an example here, and then yeah, one time in the one direction, one from the other direction, so we get precisely this corollary here. So by letting one of the sequences be constant. Okay, so we know that if a sequence doesn't yeah, go beyond a certain number, the limit doesn't go as well, which kind of makes sense in some sense, because we want something to have to be very close to the sequence, so the sequence should approach this limit. So if the sequence doesn't jump over a hurdle, the limit shouldn't jump as well. This is kind of what we would expect, so the limits behave in a nice way. Okay, let me put the next theorem. I like it so much that I will put it here separately on the blackboard. Theorem 228. And this is what is, this theorem has several names. I will always call it the squeeze theorem. Sometimes it's also called like a sandwich theorem or policeman's theorem. I think so in Italy it's called Théorème des deux carabinieri, and in French it's Théorème des gendarmes, so French policemen, carabinieri Italian policemen. I will tell you in a second why. The sandwich will then explain itself. So assume we have three convergence sequences. Three real sequences. AN, BN, CN. Real sequences. And assume that the following holds. AN is smaller than or equal to BN, smaller than or equal to CN for almost every n in n. So the sequence Bn is kind of caught between these two. And now, if we know about these outside two sequences, so An and Cn, if An and Cn are convergent and have the same limit, so limit n to infinity An is limit Cn, and this limit is called A. So if this holds true, let's take a look at this equation. So we know that from a certain point on, this always holds. So Bn is always caught between the two. And if these two guys run into the same, if these two sequences run into the same point, then this thing in between has no choice. It's caught between these two, so it has to run to this point as well. Which means if these two converge with the same limit, then Bn converges to A. So, and sandwich is kind of clear because it's kind of, this is the thing inside the sandwich, and these are the two bread slices, so it's caught in between. And the dual carabinieri is actually much more beautiful. So we have two policemen, An and Cn. So we have two policemen. In the middle, we have some guy who is arrested by them. So one is caught on the left side, one on the right side. And if the two policemen are going to prison, the guy in the middle has no choice but to go to prison as well. So this is the idea behind this. And so if something is caught between two convergent sequences with the same point, it has no choice. Proof I can start here. It's actually very simple, not simple, but very similar to the proof before. Let epsilon bigger than 0. And I won't carry out the same approach before. So as in the proof of theorem 226, you can then show that there exists in N0 such that A minus epsilon is smaller than or equal to An. Okay, and here we have got this inequality smaller than or equal to Bn, smaller than or equal to Cn, and this is smaller than A plus epsilon. Note that this time we have the same limit here, which was not the case before. So that this holds for all n bigger than or equal to n0. So if we take a look at these inequalities, we know in particular that Bn is smaller than A plus epsilon. And here we know that Bn is bigger than or equal to A minus epsilon. And if we play around with these inequalities, we first get from the second inequality that Bn minus A is smaller than epsilon. And here, if we now take this here and subtract Bn and add epsilon, we get that A minus Bn is smaller than epsilon. But the one number is the negative of the other, so this means if both of them are smaller than epsilon, then the absolute value Bn minus A is smaller than epsilon for all n at least n0. And again, since epsilon was arbitrary, this shows the convergence. So since epsilon was arbitrary, this proves the claim. Okay, so this shows this squeeze theorem. Before I give examples, one corollary, and again I want to formulate a special case that is used very often just explicitly, so you recognize this form that can really be used. Assume we have some real sequence, so let's call it xn, be a real sequence and assume that all elements are non-negative. With xn non-negative for all n and n. So, if we can find a sequence, if there exists a real sequence Cn with xn smaller than or equal to Cn for almost every n in n, and if we then know that Cn goes to 0 and limit n to infinity Cn is 0, then xn goes to 0 as well. Because this time, so on the right-hand side, we've got this sequence Cn that catches the sequence xn, and on the left-hand side, we can just take the constant sequence 0. So we are in this Carabinieri situation. So if this holds as well, then limit n to infinity xn is equal to 0. So I don't need to prove this. This is immediate. This you can immediately see. Okay, so this is a form that's really useful. And now we come to some examples and some other interesting sequences, and you will also learn a new computational trick here. Okay, we want to study the limit of the following sequence. We take the square root of n minus the square root of n plus 1 minus the square root of n. Good question. They become very big, but what happens with the difference? I mean, they each become very big. What happens to the difference? It turns out that the difference converges to 0. Okay. Now, if I had an audience here in this room, I would ask, why can't I just take the sum rule here in this case? Then I might say, okay, limit of this is somehow infinity, this is infinity, so infinity minus infinity is 0. This is the point where if a math professor hears a computation like this, he breaks down and cries, because first of all, you cannot compute with infinities like this, so forget about this always, and you cannot use the sum rule I had before, because these guys here are not convergent. The difference is convergent, but the different summands here, they are not converging. They are unbounded. Okay, so here we have to take a trick. So we cannot use the sum rule, so we have to simplify these things. And we make a following observation. For each n in n, we use the following computational trick, which is really nothing that, not too obvious, but it's nice to see. First of all, we know that this difference, the square root of n plus 1 and the square root of n, is always non-negative. This is, again, by this theorem about the monotonicity of roots, so theorem 222. Okay, this is bounded from below by 0. So we now want to bound it from above by a sequence which converges to 0, and then apply this corollary that I just wrote on the board. So if we are in this situation, we do a nice little trick. Namely, we add a fraction, we expand this as a fraction, which looks quite pointless at first sight. This is the square root of n plus 1 minus the square root of n, and now we expand this by square root of n plus 1 plus the square root of n. Okay, and then we have to divide this by the same factor to make it all work out. So, plus. This is a simple computation. So what does this matter? This is now this third binomial formula, as we call it in Germany, because we have a formula for these things. So if a plus b times a minus b, this just gives the square of the first minus the square of the second. And squares of roots, this sounds good. So we get n plus 1 minus n in the numerator, divided by n plus square root of n plus 1 plus square root of n. And now we see what happens. This is just 1 over the square root of n plus 1 plus the square root of n. And here you can, it's kind of makes sense that this goes to 0, but still we have to formally prove it. We can just estimate this from above by 1 to the over the square root of n. We simply make the denominator smaller, so this whole thing gets bigger. And this here was a special case of what we've seen before, that this is n, we have the exponent 1/2, some positive rational number, so we know that this goes to 0. And since limit n to infinity 1 over the square root of n goes to 0, or is 0 by, have I written this down? Example 223, 223. Since this is the case, and it's bounded from below by 1, we can just apply this corollary that I just had on the board. This is now behind the other one. This one here, 229. And this then tells us that the sequence in between goes to 0 as well. So limit n to infinity of square root n of n plus 1 minus square root of n. This is 0. Okay. We now want to make an even more complicated example similar to this one, but for this I have to erase. Okay, next example is a sequence which looks quite similar, but behaves more interestingly, I'd say. We take, again, this difference, square root of n minus 1 and square root of n, but this time we multiply it with the square root of n. So this is again the case where we have a sequence converging to 0, this one here, times another sequence, but this sequence is again unbounded. So we cannot apply this theorem from before to say that this might give limit 0. Before I had an example where I had a product of a sequence converging to 0 and an unbounded sequence where the result was unbounded. But here we have an interesting thing because this thing actually really converges and its limit is absolutely non-obvious, namely its limit is 1/2. And this we shall see now. Okay, first of all we use the same trick for this factor here, but I have to multiply it with an n, of course. So same trick as before. This gives that square root of n plus 1 minus square root of n times square root of n. This is the same as square root of n divided by square root of n plus 1 plus square root of n. Okay, now we reduce this fraction by the square root of n. Then we get, this is 1, and here we have to reduce both summands. So here the last one is 1, and the previous one is square root of n plus 1 divided by square root of n. So we get, again, the power laws here can be used. This is this. Okay, and now we can reformulate this, namely if n plus 1 over n, this is nothing but 1 over the square root of 1 plus 1 over n plus 1. Okay, and now here we have something interesting. So here we have that this sequence here inside the square root obviously converges to 1. So everything, all that's missing is that kind of the square root respects limits as well. This will be part of an exercise. I haven't got an exercise number yet, so by an exercise from sheet 3, the limit n to infinity of the square root of 1 plus 1 over n, this will be the square root of the limit n to infinity 1 plus 1 over n. And here we can see by the sum rule this is just 1, so this gives 1. And then we get, so simply by inserting 1, that, so limit n to infinity square root of n plus 1 minus square root of n times square root of n. This is then the limit of this thing here, and this gives 1 divided by, just by this limit rules, n to infinity square root of 1 plus 1 over n plus 1, which is 1 divided by 1 plus 1, which gives 1/2, which concludes this example. Okay, now I've made a mess with the blackboard and started just, if you should ever use a blackboard, always go from back to front when using these blackboards, and I just violated this rule, sorry. So this was this example, so I do the other example on this blackboard, and although this is mainly called, or this section is called convergence of real sequences, there is a complex example here which is basically solved by real techniques. Namely, we will show that the limit of z to the power of n divided by n factorial. And of course this could be, yeah, I mean, of course, if z is something very big, you know that z to the n, like as an absolute value, it becomes very big. That's the idea here. But these factorials, they grow so fast that this always is 0 for all z in C, which is quite a remarkable property. Okay, first of all, for z equal to 0, there's nothing to show because then this whole thing becomes 0. Okay, so we assume in the following that z is not 0. If z is not 0, so first of all, it suffices to show that something goes against 0, we need to show that the limit of the absolute value of this thing goes to 0, so that this here goes to 0. But by the standard rules of the absolute value, sorry, the layout goes wrong here, limit n to infinity, absolute value of z to the power of n factorial is 0. And this is now a real sequence, and this is what we want to tackle. And this is what we also want to use by using these squeeze methods. So we compute for each n in n, where we put an to be this term here to the n, so z, absolute value of z to the n divided by n factorial. So we do a nice computation. an plus 1 divided by an. We just compute them. Yeah, this is not apparent now why, but we will see in a second. This is now z to absolute value to the power of n plus 1 divided by n plus 1 factorial. This is an plus 1, and now we divide by an, so of course we just need to flip we need to take the reciprocal fraction, so we take here n factorial, and here we get z to the n. And of course we can now see here this and this can be reduced, and n factorial and n plus 1 factorial only differ by the factor of n plus 1. So this simply gives z to the absolute value divided by n plus 1, which we see can get very small. In particular, this gets very small, so there exists an n0 in n such that this fraction, an plus 1 divided by an, is smaller than or equal to 1/2 for all n bigger than n0, or equal to n0. And if we just multiply it with the denominator here, we get an plus 1 is smaller than or equal to 1/2 an for all n bigger than or equal to n0. Okay, so now we know how these two subsequent terms are related, and this can now be iterated. Namely, iterating this. And iterating means kind of using something again and again and again and again. Iterating this, we obtain, so an is smaller than or equal to 1/2 an minus 1. Doing this again, we can estimate an minus 1 by 1/2 an minus 2. So this gives smaller than or equal to 1/4 of an minus 2. And now we can use this again. Smaller than 1/8 an minus 3, and so on until we reach this point n0. So, and this gives smaller than or equal to 1/2 to the power of n minus n0 times an0. Yes, did I do? Yeah, okay, for all n bigger than or equal to n0. So, yeah, just to put this in terms that we can work with, we know that by definition, because there's the absolute value included, all these an are negative. So this is smaller than this is smaller than 1/2 to the n minus n0 times an0 for all n bigger than or equal to n0. So the limit of, so we need to show that this goes to 0 to have this going to 0. The limit of this one here is limit 1/2 to n minus n0 times an0. So here we've got that, yeah, this is the limit of n to infinity And let me write this explicitly, 1/2 to the power of n times 1/2 to the power of minus n0 times a n0. But this guy here, this is a constant thing, there's no n in here. So we can just do the computational rule for limits and just remove the constants and pull this out here. This is 1/2 to the power of minus n0 times a n0. This is just some real number we don't care about, times the limit n to infinity 1/2 to the power of n. And we've seen that this goes to 0 when the thing inside here has value, absolute value smaller than 1, which is here clearly the case. This is 0. So yeah, this was theorem 2.6. And so now we can apply this squeeze theorem again. So more precisely, this corollary of the squeeze theorem, but just like squeeze theorem. This gives that the limit n to infinity of an is 0. And since an is just the absolute value of the sequence that we wanted to investigate, this gives that our sequence limit z to the n to the power of n goes to infinity, that this is equal to 0, finally. Okay, this was some of my interesting examples, and yeah, next thing we will take a closer look at bounded sequences and work with them and get some nice convergence properties, and that we will do so in the next video.